and welcome to our first ever premiere release of Siemens NX. Here at Siemens Digital Industries Software, we're focused on helping our customers create tomorrow's innovations today in the most sustainable and productive way. We've got some incredible things to share with you today, so let's get into it. I'd like to start by introducing Accelerator, our integrated portfolio of software, services, and application development platform that encompasses all of Siemens Software's products and technologies. Mechanical design in Accelerator is driven by NX. NX is the industry-leading mechanical engineering solution. It gives you complete design freedom, allowing you to create and iterate on your ideas. And with NX 2007, this is the best release of NX ever. Earlier this year, the industry market analyst SimData commented that Siemens continues to innovate and reimagine CAD design in a way that truly looks to the future of design. And this shows that we're continuing to innovate, helping our customers embrace complexity and reach their productivity goals. Our customers across all industries love using NX, like Princess Yachts, who've seen significant design efficiencies using NX, enabling them to create more complex interiors and better overall designs. Or JCB, who are driving towards a more sustainable future with their 100% electric, zero emissions e-tech range. They're leveraging the digital twin to enable more consistent collaboration with a single source of data. And Red Bull Racing, working to an aggressive F1 race schedule. Through productivity gains with NX, Red Bull Racing were able to compress the time from initial design through to wind tunnel testing down to just 10 days. Productivity is a key driver for all our customers. In a recent study by Lifecycle Insights, it was discovered that more than 94% of company executives felt that either a good amount or some amount of productivity improvement was needed from their product engineering teams. Productivity and the ability to do more with less clearly affects the success of the products being designed and also the companies creating them. Taking the latest release of NX is one of the best ways to help you achieve your productivity goals. For today's session, we're going to focus on a workflow that shows you how to automatically create new parts using the all-new NX Topology Optimizer. Then we'll show you how to test and validate your parts before 3D printing. We'll be showing you how you can reduce this group of 14 parts down to just a single part and also reduce the weight from around 4 kilograms down to about 2.5 kilograms. Typically, this would have required some very manual tasks by the design engineers. But NX is helping you embrace complexity and increase productivity, whilst also helping you reduce the number of physical prototypes. So, let's get into it. Imagine we're designing a next-generation electric vehicle. In order to maximize the range of the battery system, we need to optimize the weight of every single component. In a design review of the team, the design manager identifies a group of components that could be improved. The design manager sets a target to reduce the number of components from 14 down to 1 and sets a weight reduction from 4 kilograms down to 2.5 kilograms. She creates a change request in Team Center and sends it through to the design team. And now to take you through the next stage of the demo, I'm going to hand over to Paul.
Well, thanks, Ben. Well, here I am in my NX session. It's a managed session, so I've got access to my Team Center database through Active Workspace embedded inside of NX. And I've got some tasks to perform in my inbox. Let's take a look at them. First one here is related to the gearbox bracket that Ben's just mentioned. If we delve a little further down, we can find out exactly the details of the task. And it's to use Topology Optimization study to look at reducing both the weight and the part count of the existing bracket. Now, not only does it tell me what's required from me, but it also gives me the impacted items. So if we take a look down here, you can see obviously one of the impacted items would be the overall assembly. And we can take a look at this in a bit more detail just by opening this up directly inside of NX. Let's take a look at some of the other impacted items. So again, we just go back into our Active Workspace. If I select it, notice that the corresponding geometry in the NX session is highlighted. So we have this cross-probing, particularly useful to understand the impacted items and where they fit within the assembly. And again, if I want a bit more of a level of detail, we can open this up inside of NX as well. So you can see here the bracket and the gearbox. Again, let's just open up the bracket. Now, as you can see from my assembly navigator, there's 14 components currently, so we're looking to reduce that. And if we take a look at the weight, notice that the current value is just over 4 kilos. Now, I've already got the start part of a topology optimization study done, so let's just go and find that. Again, if I go back into Active Workspace, I'm going to do a search for it. There it is there. And again, let's just open this up inside of NX. Now, what we'll do here is to go through the process of setting up the topology optimization. So again, we start the optimization feature, open it up, and we have our own environment. And one of the key things to remember about the optimization itself is that it's now an NX feature, which means that if any of the geometry changes, then your optimization feature will also change to reflect any of those modifications. Now, I'm going to perform a study, so I'm going to edit this study. There's a particular analysis type, the objective, I'm going to look for maximum stiffness. I can modify the resolution of the result. Again, you notice that the Optimization Navigator updates to reflect that. And I'm just going to hide now the original gearbox housing and shaft and the original fabricated part. But before I do that, the stages that I'm going to go through is I need to define a design space. So this is this area, or this volume, if you like, is going to contain the topology optimization study. So let's just create the design space. So again, I select the box. Notice that it automatically picks up on the material that's been predefined for that particular box. It's an aluminium, and now that's been added into my optimization navigator. Let's just hide some of these pieces of geometry we don't want to see at the moment, so I'll just hide that. And I now need to look at some construction bodies, and these construction bodies will contain geometry that you want to use as a keep out. It'll also contain geometry such as where the bracket needs to be fixed, both the chassis and also the gearbox itself. So let's take a look at the construction bodies. You can see here. Okay, there's several different construction bodies, and I'll explain exactly what they do as we go through and create them. So first things first, let's create a construction body. I'm going to group these together. So this one is going to be keep outs. Okay, and I'm going to specify these two solid bodies. So what I'm asking for there is I don't want to see any of the optimization study encroach into that particular area. I need that to be kept free of any geometry, because that's basically where the gearbox will be sitting. I'll just remove those. And now I'm left with construction bodies that are going to define where the brackets fix both the chassis and also the gearbox. And also we need to create some clearance for the shaft, so the gearbox can be dropped in to position. So again, let's create some more construction bodies. So again, we'll have another group. This one is going to be the base mounting holes, and I'm going to select these 4 bodies here to define that, and then we're going to create the fixings for where the bracket is attached to the gearbox itself. So let's again create a group for these, and again we'll select these 12 solids here that define where the gearbox mounting holes are going to be. Again, all in while you can see them being added to the navigator. And then the final one is going to be the clearance for the shaft. So again, let's just call this shaft clearance. And it's going to be a keeper. I'm going to give it an offset of 10 millimeters. again, select the body, you can see the offset's been applied, and those are my construction bodies defined. So the next stage would be to add some optimization constraints. I could add some shape constraints, but in this case I don't need to. So let's add optimization constraint. And apart from obviously reducing the part count, the other part of the study was to reduce the weight. So I'm going to specify that I need this new bracket to be equal to or less than 2.75 kilograms. I need some constraints. So every topology optimization study would require some analysis constraints. And what I'm doing is I'm going to select these 4 faces here to be fixed. Now, there's a set number of load cases that I want to add, and I'm going to specify 4 specific load cases. So again, there's a default one, but I can just add another 3 very easily. And I also want to add that fixed constraint into each of the other subcases. And it's easy to do. I can just literally just drag and drop into the subcase. So the final piece of the puzzle, if you like, is to add some analysis loads. Okay, so I can specify a vector or a component. In this case, I'm going to go for a vector, specify a value. And now I need to attach these loads to areas of the bracket. So these fixing holes, for instance. So again, I just pick on the faces and attach these loads to the one side of the bracket and then the other side of the bracket. And I would do that for each of the subcases. Slightly different load, slightly different direction, but it would be done for each one of the subcases. And then you utilize all of these subcases during the optimization study. When those were completed, I would then go into the optimizer itself and start the optimization study. Now this took around 5 or 6 minutes to do. I'm not going to do it here in this, live in this particular session, but I do have one that I've already completed, and we can take a look at that. So let's remove the construction bodies. Let's bring back the gearbox housing and the shaft, and bring back the one that I've already completed. And there you can see it. So again, I've got that clearance that I've set, so I could bring the gearbox in. I've got that all those key part areas as you noticed again, so there's no geometry inside of here. And I've got the construction bodies that I used for the base mounting holes and the gearbox holes included in there.
Later that day, Paul, who is in the UK, calls Jeff, who's based in the US, to discuss some design simulation for the new part.
Hey Jeff, how you doing?
I'm good.
Hey listen, I've got something I'd like you to take a look at. It's a topology optimized part. It's a gearbox bracket. So I'd just like you to check it and validate it that it's fit for purpose.
Okay, I can see your screen now.
Okay, so you can see that it's it's an interesting shape. It was optimized. I just want you to check out that there's no areas of concern that we need to be aware of.
Okay, I have a good idea of how I can analyze this. Let me take a look, and when I have some results, I will give you a call back.
Appreciate it. Thanks very much.
Yeah, you're welcome. Anytime. Follow me along to perform a design analysis so that we can give Paul the feedback that he needs. We will start by loading the optimized part, which is a convergent body, from the server. We will use an application inside of NX called Pre-Post to perform the analysis. We will create 3 files to contain all of the CAE data that we will be generating. The SIM file will store information such as loads and boundary conditions. The FEM file will contain our nodes, elements, and material data. An idealized part is created as a duplicate of the CAD model so that we, as an analyst, can make changes without disrupting the workflow of the designer. Next, we need to assign a material to the part and then generate a 3D mesh. I like to click on the lightning bolt to get an approximation of the recommended mesh size. Don't go any larger than this, as it can make for a poor quality mesh. A reasonably smaller number than the recommended size will give better results without forcing the solution to take too much time. Now we need to create a rigid element with its base node at the approximate location of the center of mass of the gearbox that attaches to this mounting bracket. We don't need to be exact for this analysis, as we are only trying to provide baseline guidance to improve the quality of the design. Use the between 2 points method to get an approximate location. Now that the base node of the rigid element has been created, we will connect it to all 12 of the mounting holes on the bracket. Now we will move on to the simulation to create our boundary conditions and to solve our model. Our boundary conditions consist of constraining the bracket at the 4 mounting locations. The load is applied at the approximated center of gravity of the gearbox. It is meant to imitate a force of 3 times gravitational acceleration in the direction of travel of the vehicle. The mass of the gearbox is used in the magnitude of the force. Solve your model using the integrated SimCenter Nastran solver. This should only take a couple of minutes depending on what kind of computer you are solving on. Now comes the reason for performing the analysis, evaluating the results, and giving recommendations to your CAD designer. When displaying stress results, it is a good idea to turn off any elements that are not needed, clean up the display by turning off element edges, setting the results to average at nodes, and finally changing the scale for effect. Let's interrogate the CAE results so we can make recommendations to Paul. Every structural analysis will indicate the locations of maximum stress with a red color contour. You will see a few areas in the model that have a color red. But we do not need to be concerned, as the overall magnitude of the stress is very low. The results indicate we have a good design that will be able to handle the performance requirements for the part.
Later that evening, after Jeff has finished his simulations, he gives Paul a call to share the results.
Hi, Paul. Okay, are you seeing my screen?
Yes, I am.
Okay, so I just wanted to point out a couple things. First of all, when I zoom in on the 4 mounting holes, you're going to notice the red spots. You can ignore that because that's just a result of the way that I set up my model. So those are artificially induced high stresses based on the boundary conditions. But what I did when I interrogated the model and looked at the results, I do see that the overall stresses in the rest of the model is very low relative to the endurance limit for the material. So I would say that you're okay from a structural performance standpoint.
That's good to hear. But,
all right, well,
thanks
great.
again.
Yeah, thanks. It's always good to work with you.
Back at the office, Paul begins implementing the changes recommended by Jeff.
So the next stage of the process is to start to document the model using model-based definition, and in particular, product and manufacturing information, or PMI. So I enter the PMI application. I have a number of commands that are available to me to document the geometry. Typically, I'd select one of the commands and start to pick geometry off of the topology optimized result. But in this first instance, I'm going to use one of our pre-configured rules. These automate the ability to apply PMI to the model. So in this instance, I'm going to look at creating the size on all of the holes in my model. I invoke the rule. It's now intelligently searching the model to find all of the holes within the part and applying the PMI information directly to it. And as you can see, it's found the 12 holes that connect the bracket to the gearbox, the 2 large holes through which the shaft passes, and the 4 holes that are used to connect the bracket to the chassis. Now, as I said, there are a number of other commands that we can use. So if I want to add further PMI, again, I can just pick geometry directly off of the model. Okay, we're going to add some tolerance to that. And again, it's as easy as that. I'm just literally picking geometry straight off our optimized result. So we could continue, obviously, to completely and fully document the model, but you get an idea in this demonstration of some of the power of being able to apply and fully document a model with PMI, either manually or with one of the pre-configured rules that we have at our disposal. The final part of this demonstration, or this section of the demonstration, we're going to replace the existing bracket with this new optimized model. So let's take a look at doing that. Okay, we'll pull up our subassembly that contains the bracket, the original bracket. And the first thing I want to do is to remove that. I can also remove these other components. Let's add our single piece bracket in. We know the part number. Let's see, we've got a thumbnail of that. Let's snap that to here. Just position it like so. And then we can use the assembly constraints. And there we have it. Our part is now being added in to the original assembly. If we take a look at the top level, again, let's just take a look inside. You can see that our new bracket fits nicely within the overall assembly. I've completed my tasks. I've done the topology optimization study. I've then done some modification to the result, adding some NX features, adding some PMI, and now I'm going to hand it over to my colleague Ashley, who's going to check to make sure that it's 3D printable. So I'm just going to give him a call.
Hey, Paul.
I've just done a topology optimization study on this bracket for the gearbox for the vehicle. I think it's come out rather well, but I'd like for you to take a quick look at it.
Yeah, okay. So like a little validation just to make sure it's printable, and I guess we should throw it into a build tray, create some support structures. And we're planning on doing this on a Renishaw, right?
Correct, yeah, that would be really good.
Sounds great. No problem. Take care. Bye. Hi, everyone. So Paul's given me this really great topology optimized part that he sent over. It's for some sort of motor mount, gear mount, gearbox mount, that sort of thing for an automobile. And so we're going to print this part using aluminum and additive manufacturing. The problem here is that additive manufacturing is really accurate these days, but it doesn't always produce parts that are accurate within tolerance. And if you want exact surfaces within some really tight tolerances, then you often need to print your part and then send it on to a downstream machining step. And that's what we're going to do here. Now, to do that, I need to alter this geometry a little bit so that it has the material it needs for the post-print machining, so that we can machine those parts away and get the exact surfaces we need. So I've got to print a part that's not exactly the part that Paul sent along, but sort of an interim version of the part. And then when Joe gets the part and does the machining, he will machine it back to the exact surfaces that Paul has designed. Now, the great thing about this particular part is that it came out of our new topology optimization system, where we get actual faces inside the model. So I've got my selection here turned to face, and you can see that straight out of topology optimization, we've got things like these holes have actual faces, and these planar regions are actual faces. So that makes it very easy for me to go through and do the modifications I need to do to get this part ready for printing. If I was doing this with geometry from some other topology optimization system, I would most likely be just sort of massaging facets. And anybody who's done that knows how terrible that is, even with a really good system. So in this case, we're getting really nice, clean geometry out with real faces I can work with to do my job easily and cleanly. And I'll show you how right here. First thing I'm going to do is take these holes down here at the bottom that are pretty large, and I'm going to shrink them a bit, give them just a little bit more meat, so that when Joe comes along with his machining process later and drills those out, he has enough material to work with to drill it out and get the exact surfaces we need. So I'm going to go to my offset tool here, and I'm just going to select the face and tell it to automatically find the rest of the faces, and I'm going to bump those in by about 5 millimeters. So basically I just shrunk those holes with one step. It took me about 10 seconds in our new system, which is, again, if you do this with facets, this is just amazing compared to that. These top holes I'm just going to get rid of. They're small, and again we need some meat up here, so I'm going to tell it to loose match those. It's going to find all 12. Those I'm just going to get rid of. We know where they're at, we know what the diameter needs to be. I'm just going to fill them in, and we'll have those ready for machining as well. The final step is down here on the bottom. We have these 4 sort of feet, and we want those to be all perfectly planar so that when we mount this in the car, it's not going to wobble, it's not going to torque and have any undue stress put on it. We want those to be perfectly planar. So again, we're going to build up those surfaces just a little bit and machine them back so that they're perfectly planar. I'll use the move command to do that, and I'm just going to pick each one of these faces here, and I'm going to move them up by about 2 mils to give us enough material to machine away. Hit OK, and again, this is all done, what has it taken me, 2 minutes maybe to make all of these edits? If you were doing this with a system where you had to just edit the facets, you would not be doing this in 2 minutes. This would be a project. So you can see how easy it is in our new system with the new topology optimization, the types of geometry it returns to get a part prepped for printing. The next step is to put that into a build tray, so I'll be back in just a minute and we'll do just that. So we now have a part that we've designed for additive manufacturing. We've manipulated the geometry. Now we need to put it into a build tray and get it set up for printing. So I'm going to go over this part where I have basically an empty part. I'm going to select my printer, and then I'm going to add the part to the build tray. Now I don't really care where this part comes in. It's probably going to be thrown out in space wherever it was in its native assembly at the moment. But I don't really care because I'm going to take that part and I'm going to run it through a new system we have for correcting for distortion. So one of the real problems with additive manufacturing, especially metal additive manufacturing, is distortion. Now that can throw a part out of tolerance. It can even cause failures within the print where you end up with a really expensive door stop. Lots of these things can be mitigated by controlling the distortion that the part goes through as the little bits of metal and the different layers of the part are heated up and cooled down within the printing process. Now, a lot of distortion problems can be alleviated by orienting the part in the proper orientation. And we have a tool that allows you to do that called the NX Build Optimizer. Now, in the latest release of NX, we have integrated that tool into the NX system, and it's up here under the analysis menu. If you go to more and say thermal distortion, you can invoke this tool. Now, what this does is you pick your part, and the tool will take your part with a couple of characteristics you hand it here. It will upload your part into the cloud. It will run 100 different orientations of the part, running a simulation for distortion on each one of those orientations, and hand you back the orientation that has the least amount of distortion possible. And then you can move on to building things like support structures and all the rest of the things you need to do to print. But this is one way to really help the initial print quality for parts without having to go through some, really trial and error type operations that have been done in the past. So I'm going to go ahead and invoke this system. It's going to go run and do about 100 different orientations, and it's going to come back with an orientation for me. And then we'll do a few more things to it and get it set up for printing. So I'll be back in just a minute. So the system's come back, the AM Build Optimizer's come back, and it's given me this orientation as the orientation that it believes will give me the least amount of distortion. So now the last thing to do here is to create supports. Now I've gone over here in my support structure library. I've got a bunch of supports created here under this new support profile for blocks and cones and tree supports and all those sorts of things. And you can see that reflected over here in the dialog. Now I can do automatic supports, which we'll do here in a second. We also have the option to do manual supports where I pick the areas that I want. The system finds the areas to support and I pick which ones I actually want to be supported. I can do regions only where I make regions that are supported, or I can do automatic, which is what I'm going to do here, where the system finds the regions it thinks needs to be supported and supports them. So I'll select my part. I will get a preview, basically showing me these red areas down here where the part needs to be supported, and I'll say OK. And the system's going to go through and it's going to create support structures for my part so that when this part is printed, it's not going to sag or distort or have any effects of gravity on it, like you might see if you didn't support it properly. Now, it's not going to maybe support all of those red areas it showed me. It's going to do a further analysis once I hit OK, further analysis in the preview, so I may get a warning here saying that some areas didn't actually need support. Yep, just like that. But now we have a completely supported part. I can take this part, I can set up my build strategy for my printer, generate the actual print commands, send those to the printer depending on which printer type you have, all directly inside of NX. And sometimes, depending on the printer, again, I can also look at the build processor manager and open even slices to understand what each slice, what each layer of my print's going to look like, all from within inside the system, no STL files to drop, and all completely integrated from beginning to end. So now I've got this part, I'm going to send it off to the printer. Once it's been printed though, Joe has to take over and do the machining steps to bring that part back to the actual part that Paul designed by putting those holes back in and machining those surfaces back. So I'll pass this portion over to Joe.
Meanwhile, while the part is printing, Joe starts to prepare for the final machining processes.
For this part of the demo, I'll be taking this really nice organic looking additively manufactured bracket and putting it into the NX manufacturing application to do all the finished machining. The component you can see here is the part that was designed by Paul using the latest Topology Optimization technology, but I'll also be working with the data that was created in the AM application by Ashley, and this will be the physical condition of supply that the shop floor will be receiving to machine. Let me change the view to show you all the components I'll be using for the final machining within NX CAM. We have the design part. This is what we'll be machining to. Here is the condition of supply part, which Ashley defeatured in the AM application, and this is the part we'll be machining. We've got the standard vice fixture for the machine tool, and we've also got this custom fixturing to hold the AM component. Because the part is not very prismatic and is very organic in its geometry, it's important that we design the correct fixturing to hold the component in the correct orientation for machining. These fixtures can be additively manufactured at the same time as the additively manufactured component, or machined in situ on the machine tool itself. So let's jump into CAM and take a look how I finish machining this component. This is the manufacturing setup that I've created. You can see that we're working in the context of the machine tool. It's really important to work within the context of the machine tool so that we can validate all the kinematics and simulate the machining the part correctly and accurately. You can also see that we've got our component mounted in the custom fixturing, which in turn is located in the standard vise that clamps directly to the bed of the machine tool. A real benefit of NX CAM is having access to what we call Posthub. Posthub is a platform hosting an extensive library that we can log into and download one of thousands of post processors available to us to meet the needs of your machine tools on the shop floor. Here we have the Smart Machine Toolkits. Smart Machine Toolkits not only give us a working post processor, but also give us the full machine tool graphics and a simulation driver which enables us to validate and simulate the NC code. So for this example, I'll choose the HAS UMC and simply and dynamically download that Smart Machine Toolkit directly into NX. Next, we'll take a look at the machine operations required to finish machine the key features of this additively manufactured component. The machine operations are really simple to create in NX and work really well with the data that came directly out of the additive manufacturing environment. Let's take a look at the first 2 milling operations that we're going to use. Firstly, to remove the extra material from the part, I'm going to use a dynamic roughing toolpath. And secondly, a helical hole milling toolpath to open up the holes. Let's take a look at the material being removed so you can get a better understanding of how CAM toolpaths work. So, with minimal input, we're able to create these really optimized machining toolpaths to remove the remainder of material from the bottom of the hole of the additive component. Using the same tool, we can then open up the hole from the reference size that came off the printer itself to the finished design size of the component. The next thing we need to do is look at the 12 holes that need to be drilled and machined to finish size. You can see we've got some PMI attached to these 3 holes. These 3 holes have a tolerance against them, a limit of fit in fact, because they're locator holes and require a tighter tolerance to fit dowels during assembly. What I'm about to show you is process automation within NX CAM. What NX CAM can do is look at the features on our component and decide which tools and which operation types are best suited to machine those features. As well as that, NX will read in the PMI data and tolerances to directly influence which operations are needed to meet those tolerance requirements. Let's take a look at these features in the Feature Navigator. As we can see, NX has found all 12 of the holes and identified 3 of them as having PMI data against them. If we take a look at the holes without PMI, we can see that these 3 holes, NX has decided to create a spot drilling operation followed by a drilling operation, and the drill will be the finished size to finish the hole. Let's take a quick look at those operations being machined. Firstly, we see the spot drilling, followed by the drill, and that drill will finish those holes to size. If we go back to Feature Navigator and take a look at the holes that have PMI attached to them, and if I go and find the related operations, this time you'll see that NX has created 3 machining operations. It's created a spot drill operation to spot the holes. It's created a drilling operation using a slightly smaller tool this time, and then it's finishing the hole size with a boring tool to the tolerance that the PMI has defined. And this is a great example of how intelligence from the design side of NX can drive the automation of the manufacturing side as well. Let's take a quick look at what that looks like. So again, we can see the spot drill, followed by the drill, again, drilling slightly smaller. And finally, we can see the boring tool coming in and finishing the diamond for those holes to the tolerance. So finally, let's take a look at how we validate the program that's being created. It's really important that the NC code that's going to run on the physical machine on the shop floor can be validated and checked to ensure that there's no gouges, no collisions, and that the tool path is of a high quality. To do that, we utilize our machine tool simulation. Earlier on, we downloaded the Smart Machine Toolkit, which contained the machine graphics to give us context of the machine, as well as the post processor, so that we can output to the machine tool that matches what we have on the shop floor. But what it also gave us was a simulation driver, and that simulation driver is going to verify and validate that the toolpath is collision-free and safe before we use it on the shop floor. On the right-hand side of the simulation, you'll see that the post-processed NC code is running down in just the same way as it will on the CNC controller. And that NC code is driving the machine tool kinematics in NX to give a true digital twin validation of the CAM program, including material removal and a much more accurate machining time. NX is the only CAM tool that offers integrated NC simulation and is a fantastic way of validating and ensuring a safe collision-free toolpath. This concludes the portion of the demo regarding the finished machining in NX CAM. And what we've seen today is how we can take both data from design and also data directly out of the AM application to create custom fixturing to hold that component and to validate the NC program that has been created to finish machine these components.
Now that the part is printed and machined to its final dimensions, we can assemble it back onto the vehicle. So, we've covered a lot of ground today, from topology optimization through simulation to additive manufacturing and CAM. To learn more about the rest of the new capabilities being released in NX 2007, head over to the NX Design blog. Simply go to blogs.sw.siemens.com or scan the QR code using your smartphone. Whether you're an experienced NX user or learning NX for the first time, I'd invite you to head over to the NX Design community. Simply go to community.sw.siemens.com or scan the QR code and you'll find lots of like-minded users ready to help. And of course, the NX Design team is also there to answer your questions at all times. Finally, you can try NX for free for 30 days using our cloud-connected trials. Head over to trials.sw.siemens.com or scan the QR code to check it out. Thanks again for joining us today for the first ever live launch of Siemens NX. We'll be hanging out in the chat, so continue to post your questions and we'll keep answering them. And once again, thanks for watching, and we'll see you in the next one.